Hello everyone. So, we will continue with the topic testing of functional textiles. So, the course is testing of functional and technical textiles. In first part we are discussing the different aspects of testing of functional textiles. In this segment, first we have discussed low stress mechanical characteristics. After that, we have started the transmission characteristics. In transmission characteristics, we have already discussed the transmission of air, transmission of moisture in the form of liquid and in the form of vapor. We have discussed various test methods to evaluate all these characteristics. So, after air transmission and moisture transmission, now we will discuss the method of measurement of thermal transmission. So, there are different methods available. So, before going to the measurement techniques, we will discuss basic aspects of measurement. So, measurement of thermal characteristics we will discuss in two conditions. One is in normal condition, where we will discuss the thermal transmission measurement for normal clothing, considering the temperature is in normal condition and skin temperature is around 35 degree Celsius. In addition to the normal condition, we have another condition which is extreme condition, like extreme cold condition and extreme heat condition, maybe in flame or radiant heat. So, the measurement techniques for extreme conditions are entirely different from that of normal condition. We have different measurement techniques. So, we will discuss all these one by one. So, before going to the measurement techniques, first let us discuss the thermal transmission parameters. There are various thermal transmission parameters. Before we understand the testing methods, we must understand all these parameters clearly, then we can interpret the data. So, the thermal resistance is the basic parameter which we must understand. Okay. The thermal resistance of textile material is measured in SI unit in terms of degree Kelvin square meter by watt. So, what is this? So, it is basically it is defined as the ratio of the temperature difference between two phases of fabric in degree Kelvin to the rate of heat transmission in watt per square meter. That means, degree Kelvin divided by watt per square meter, it is coming as degree Kelvin square meter by watt. So, the reciprocal of heat flux is the thermal resistance, and heat flux is measured with the unit of watt per square meter per degree Kelvin. So, the ratio of the temperature difference between two phases and the rate of heat transfer per unit area is basically it is the thermal resistance. Now, a practical unit is also there. So, practical unit of thermal resistance which is widely used, it is a TOG, which is 1/10 of the SI unit. So, 1 TOG is equal to 1/10 square meter degree Kelvin per watt. So, the TOG is simply 1/10 of the SI unit. Another practical unit which is very widely used specifically for cold climate clothing, which is known as CLO. So, this is actually approximately equal to 1.55 TOG. So, we will see how we can reach to this conclusion, this relationship with some basic assumptions. So, there are various parameters used to express the heat exchange between human body and its environment through clothing. So, these parameters are MET, CLO, TOG. So, we must understand all these parameter very clearly, then we can use this parameter, these units for different application. First we will discuss the MET. Basically MET is nothing to do with the clothing insulation. MET is actually it is a metabolic heat. It is derived from metabolism. So, MET is used to quantify the metabolism of a man resting in a sitting position under condition of thermal comfort. Okay. Now, if we see this table here, in the first column it is showing different activity level, and in the second column it is a metabolic heat generation, it is giving in watt per square meter. Now, as per the definition of MET, where it is mentioned that the man is resting in a sitting position. So, we can use the value of seated quietly, which is around 55 to 65 watts per square meter, and we can take the value 58.2, that means, so 1 MET is equal to 50 kilocalorie per square meter per hour, or it is coming out to be 58.2 watt per square meter. So, when it is 55 to 65, so we can take 58.2, that means 1 MET is equal to 50 kilocalorie per square meter per hour. So, that is 1 MET. That means, a person when he is sitting quietly, so he is generating a heat which is 50 kilocalorie per square meter hour, and that is he is generating 1 MET. Now, next parameter which is CLO. Now, CLO is directly related with the MET. So, CLO is the measurement of clothing insulation. So, clothing insulation is expressed in terms of CLO. So, how is it related with the MET? Let us see. 1 CLO is defined as the insulation of a clothing system that requires to maintain a sitting resting average male comfortable in a normally ventilated room. That means, in sitting resting condition, a male is actually generating one mate. Once he is generating one mate, to keep him comfortable, the level of insulation which a clothing should actually have, that is called 1 clo, and the room condition, the ventilated room condition is expressed in terms of 0.1 meter per second air velocity, and air temperature is 21 degree Celsius, and the relative humidity should be less than 50%. That is the condition of room. Now, using few assumptions, we can derive the relationship. Now, the assumption is that 24% of the metabolic heat is lost through the evaporation process from the skin and respiration. That means, this 24% of the metabolic heat is lost where the fabric is not coming into picture. So, 24% of 50 kilocalorie per square meter per hour is coming out to be 12. 12 is the heat which is lost through evaporation and respiration, and remaining 38 kilocalorie per square meter hour transmitted through the clothing. So, 38, that much heat is required to be transmitted. The clothing insulation should take care of that much heat, 38 kilocalorie per square meter per hour. Now, going further, so remaining 38 kilocalorie per square meter hour should be transmitted through the clothing assembly by conduction, convection and radiation. These are all dry heat. We are not talking about the moisture vapor. The comfortable mean skin temperature is 33 degrees Celsius, that is actually taken from the literature. Therefore, the total insulation of clothing, that is clothing insulation plus the ambient air layer insulation, which is given by I total, IT insulation total, which is equal to 33 skin temperature minus 21 the ambient temperature, that is the temperature gradient, divided by the heat which has to be actually transmitted through the clothing. So, which is coming out to be 0.32 square meter degree Celsius hour per kilocalorie. So, that is the amount of heat which is to be transmitted, and this heat includes the air insulation. This much insulation is actually including the air insulation. Now, let us consider the insulation of air is 0.14 square meter degree Celsius hour per kilocalorie, that is the insulation of air. So, insulation of air and insulation of fabric, they are in series. So, we can simply subtract from the total insulation. So, we will get the fabric insulation. So, insulation of clothing is 0.32 minus 0.14, it is coming out to be 0.18, which is the insulation of clothing, and that is actually the, by definition it should be 1 clo. So, 1 clo unit is defined as 0.18 square meter degree Celsius hour by kilocalorie, or if we want to convert into watt, so we must divide by 1.163, it is coming out to be 0.155 square meter degree Celsius per watt, okay, which is known as effective insulation. So, effective insulation of clothing is 0.155 and this is the unit of SI unit. Now, we can get the value. So, TOG is also unit of thermal resistance of clothing and is defined as the thermal resistance that is able to maintain a temperature gradient of 0.1 degree Celsius with a heat flux of 1 watt per square meter. That is 1 degree temperature gradient, the heat flux will be 10 watt per square meter per degree Celsius. So, for 0.1 it is 1 watt per square meter. So, for 1 degree Celsius it will be 10. So, that means the reciprocal of the heat flux is TOG. So, 1 TOG is equal to 1 by 10 square meter degree Celsius by watt, which is SI unit. That means 1 TOG is 1/10 of the SI unit, that 1 kilo is 0.155 of SI unit. So, 1 kilo will be, this is multiplied by 10. So, 1.55 TOG. So, that is the relationship, 1 kilo is equal to 1.55 TOG. So, here we can derive the relationship between mate, kilo and TOG. So, we have understood this relationship. Now, we will discuss different measurement technique, where we will use all these units for better understanding. So, let us first understand the application of kilo value. So, as I have mentioned, the kilo unit is the clothing insulation, which is extensively used for the practical, as a practical unit for extreme cold climate clothing or any cold climate clothing, or even we can use this for heat, extreme heat clothing also. Now, the picture shows that this person without any clothing, that means he has the kilo value 0. So, as the person is actually putting on the more and more clothing, the kilo value is increasing. That means the kilo value is simply addition. So, he is actually wearing a T-shirt and say half pant. So, here if we know the kilo value of T-shirt and this half pant, so it can simply be added. So, the example here it is given. So, insulation for entire clothing system is the summation of individual component. So, a person who is wearing a half shirt and all these components, if we simply add, it will be the total kilo. Here the all these things 5 components are added and we are getting total kilo value of this entire system as 0.38. Now, if we talk about this, here kilo value with this system it is 0.91, it is approximately close to 1. That means a person who is generating one mate, he will have to wear this type of clothing to keep him comfortable. That means the heat generation and heat release will be balanced. Now, this is the curve which is known as IREQ, that is required insulation. So, the calculated required insulation value can be regarded as a cold stress indicator. So, this cold stress index is basically it is nothing but it gives us direct indication of the level of cold stress. Now, this let us see this diagram where x axis shows the ambient temperature. In this picture it starts from minus 40 degrees Celsius, minus 30, minus 20, minus 10, 0, plus 10. So, these are the temperature, and IREQ value, that means required flow value of the clothing to maintain, to keep the person comfortable. Here it is given in y axis. What does it show? Suppose a person who is actually at the temperature of minus 20 degrees Celsius, and he will require different level of flow value depending on his activity. Suppose at minus 20 degrees Celsius he is resting, that means if it is around this zone he needs a clothing with a flow value of 6.5, around 6.5 flow value he will require. But the same person, if he is working very hard at that temperature minus 20 degrees Celsius, he will require a clothing with flow value less than 1. That means, at minus 20 degrees Celsius, if he is sitting idle, he is resting, he needs a large quantity of clothing, many layers of clothing, different types of clothing, but the same person will require relatively lesser number of clothing layer if he is working very hard. So, depending on the activity level, so if he is gradually becoming active, he will require less insulation in clothing. So, figure shows IRQ value for low physiological strain. Low physiological strain means he is relatively in comfortable position. So, IREQ value needed to maintain low level of physiological strain, neutral thermal sensation at varying temperature. So, at different temperature he needs different level of clothing insulation. Suppose the same person working same level of activities, like suppose he is working very hard, if he is been shifted to another location where temperature is minus 30 degrees Celsius. So, to keep him comfortable he will require little bit higher flow. So, accordingly the flow can be adjusted and we can select the clothing accordingly. Now, the calculated required insulation value can be regarded as the cold stress of a person. Using REQ comprises of 3 evaluation steps. First, we have to determine the REQ for given exposure condition. So, from using this graph we can select the REQ value, then comparison of REQ with protection level provided by clothing. So, we know the level of REQ required, then we have to compare this REQ with the clothing REQ value, clothing flow value, determination of exposure time if protection level is of lesser value than REQ value. So, that means if our clothing protection level is less, that means suppose we need the CLO value REQ value 4, but we have a clothing say with the 3.5 CLO value. In that case, we have to know the exposure time. So, if the exposure time is less, then we can little bit safely use that, but if the exposure time is very high, very long exposure time, then we should not take any risk. The IREQ indicates a protection level. The higher the value, the greater the risk of body heat imbalance. That means, a person who is at say REQ value 2, he will have lesser threat from cold injury than a person who is at say 6 REQ value. The two levels of strain correspond to a lower level, that is neutral condition, and higher level slightly cold condition. Here if we see, for each and every condition we have two levels, one is high level and another is lower level. Suppose a person at minus 30 degree Celsius doing light work, his REQ is say 3.5 to 5. So, 3.5 to 5 means if we have a fabric or clothing system with 3.5 CLO, he will be actually with a 5 CLO, he will be basically comfortable, but if he has 3.5, he will feel little bit cold stress. Now, these are simple guidelines, these are available in published literature. So, we can have different combination. So, we have to simply select the combination and we know the total CLO value of all these combinations. So, we know, like for example, briefs, short sleeve shirt, fitted trouser, calf length sock and shoe. A person if he is wearing that, then his REQ value will be, the CLO value will be 0.5. So, accordingly we can select the combination, we can have different combinations. So, few combinations are given here. Now, few other parameters, the insulation value of fabric is measured by its thermal resistance, and thermal resistance is reciprocal of thermal conductance. What is thermal conductance? Thermal conductance is expressed in terms of watt per degree Kelvin. Watt per Kelvin is measured by measuring the total heat transmitted in kilocalorie through fabric per unit time with unit temperature difference. So, that is a thermal conductance, and conductivity is due to both the fiber and entrapped air. So, thermal conductivity is mainly through the fiber material and through the air, and it is expressed is that thermal conductivity, its lambda, the unit is watt per meter per Kelvin, can be, that is lambda equal to 1 by thermal resistance R multiplied by D by S. Okay. D is the basically thickness and S is the unit area. So, the measurement of heat transmission in a particular direction has practical difficulty. It is not like a fluid like air or water. Now, let us first see, as we have seen earlier, that if we want to measure the air flow, in a particular direction. So, in this direction we want to measure air flow, what we have to do? We have to flow the air through a pipe, and this air will flow out, and we can measure the air flow rate in terms of say liter per say hour. And here we can guide the air through this pipe or through any channel. So, any of any form we can guide the air or any fluid. So, in case of say liquid also, we know this channel and we can measure the flow rate. Okay. But if any heat we have to transfer say through a fabric, we want to measure the heat flow rate through fabric. If we want to measure the air flow rate through fabric, so we can cover this side, other side of the pipe or the tube with the fabric, and we can measure the flow rate. Similarly, for liquid also we can measure the liquid flow, we can just cover this other side of fabric and we can measure the flow rate through the fabric. But the heat, the problem of heat transmission is that heat we cannot have the flow in the one direction, it cannot flow in unidirectionally. If a heater, if it is the source, it is a heater, the heat will always try to flow in all the directions. So, if we want to measure the heat transmission only through the fabric, it is very difficult, because the whatever heat it is actually generating, it is a portion of the heat is transmitting through the fabric, but rest heat are in other directions. So, it is very difficult to quantify this amount of heat which is through fabric. So, we have to use some alternate arrangement, it is some indirect arrangement to measure the heat transmission through fabric. So, typically two approaches are being used. The approach one is that comparison of unknown sample characteristics with standard sample. So, if we can compare the thermal resistance of unknown sample, that is our fabric, with standard sample, in that case we can measure the thermal resistance of a particular fabric. Now, here suppose we want to compare the unknown sample with a known sample. So, this is one known sample, say plate, standard plate with known thermal insulation value, thermal resistance value is known. Another unknown sample which is placed in parallel, it is in series, we are placing just above the known plate, this is fabric which is unknown sample. And here if we want to measure the thermal insulation of this fabric. In that case, we have to measure the temperature here, temperature at junction point T1, T2 and T3. So, the temperature difference between the surface and the ratio of thermal insulation, thermal resistance, this ratio is constant when the materials are in series. That means, R by say T1 minus T2 equal to R of standard, R of fabric. So, R F will be say T2 minus T3, where T1 is more than T2 is more than T3, because this is the heat source, heat is flowing through this. So, using this R standard, so using this simple basic equation, we can calculate indirectly the thermal resistance of a fabric. So, this technique is used in TOG meter, this principle is used in TOG meter. Another way of measurement is that to reduce the heat loss in other direction. So, if we can somehow direct the heat towards one direction and blocking the heat in all other direction, so that we can channelize the heat only through the specimen and we can measure the thermal transmission directly. So, fabric thermal conductivity, as we have already discussed, it is expressed by this formula. Now, first we will discuss the principle of TOG meter. So, TOG meter, we have two types of TOG meter, one is the double plate TOG meter, two plate TOG meter, another is single plate TOG meter. So, standard and test samples have to be placed in series. As I have mentioned, the internal resistance of test fabric is calculated by comparing the temperature drop across the test fabric and the standard fabric, that is standard may be fabric, or in this case we can use the standard plate. So, two types of TOG meters are there, two plate TOG meter and single plate TOG meter. Now, this is the schematic diagram of two plate TOG meter. There is a bottom plate which is heated by the heat flow. Just above the bottom plate we can place the fabric specimen, and another plate, that is top plate, is used, which is lower mass, lighter in mass, which is used in just above the fabric. The mass should be lower, otherwise it will compress the fabric specimen and the insulation characteristics of the fabric will change. So, as I have mentioned, the ratio of the insulation and temperature difference, they remain same, and that is the ratio of say insulation of fabric, R fabric, divided by the temperature difference between the two surfaces of fabric, that is the T2 minus T3, which is equal to R standard by T1 minus T2. T1 is the bottom side temperature and T2 is the top side temperature of the standard plate. The sample is placed between heated lower plate and insulated upper plate. The upper plate should be of low mass, so that fabric should not get compressed. The temperatures T1, T2 and T3 are measured. So, T1 is the temperature measured at the heater, T2 is the temperature between standard plate and fabric, and T3 between test fabric and upper plate. The heater is adjusted so that the temperature of the upper face of the standard plate T2 is exactly same as the skin temperature, which is around 35 degrees Celsius. So, after the two plate, now we will discuss the single plate togmeter principle. In single plate, we simply use one standard plate. Here top plate is not used. So, the temperature at the heater, that is at the bottom of the standard plate T1, and the temperature between the standard plate and fabric T2, and the temperature T3, which is the temperature of the air, ambient air, which is typically above 1 meter of the fabric specimen, where the temperature is actually standard. The sample is placed on the heated bottom plate and the top is left uncovered. The air above the specimen has a considerable thermal resistance. So, it is the summation of the insulation of fabric and air. Okay. So, that actually we will measure here. The temperature T1, T2, T3 as I have already mentioned, where T1, T2 are same as that of two plate togmeter measurement, and T3 is the temperature of air, that is the room temperature. A separate experiment is therefore performed, because the insulation which we are getting here, it is the insulation of air and the specimen. That is why we need to conduct a separate experiment without the specimen, that is called bare plate test, to measure the resistance of air, which is expressed as R air. That means, whatever value we will get with the sample, if we actually subtract the R air value, we will get the exact value of the fabric insulation. So, in case of bare plate, it can be calculated as follows. So, as we have seen earlier also, okay, R air is the thermal resistance of air and R standard is the thermal resistance of standard material. So, the experiment is repeated with the sample placed on the bottom plate, and the apparatus is again allowed to reach its equilibrium. The thermal resistance of the sample is actually calculated by subtracting R air value. So, these are the two methods which are actually used for measuring the insulation of fabric in actually comparing by knowing the standard plates resistance. Next is the guarded hot plate. The guarded hot plate principle, it works with the principle where we try to control the direction of heat flow in a particular direction, where it only goes through the fabric specimen. The thermal transmission is measured here, the parameter which is called thermal transmittance of fabric. Thermal transmittance is reciprocal of thermal resistance. In this apparatus, a test plate which is surrounded by a guard plate at 4 sides. Okay. Now, let us see, suppose this is test plate. Okay. Test plate. Now, we have to heat, this is a heater 1. So, the heater 1 is heating the test plate, and suppose we are placing the fabric specimen on this. This is the fabric specimen, and what we want? We want to measure the heat which is flowing through the fabric, and the heater 1 is heating the test plate, but this heat is transmitting through other direction also. So, it is very difficult to know how much heat is getting transmitted through the fabric. So, the guard plate, guarded hot plate principle, where we would like to direct the heat in to pass through a particular direction. Here the heat which is flowing in other direction, say in sideway direction, we can block the heat by providing some insulation, some cork insulation we can provide. And this plate, if we see from the top side, this is the plate, so test plate, okay, test plate, and the insulation is provided at 4 sides. These are the insulation, so which actually prevent the heat flow in sideway direction. But this insulation may not be sufficient, the heat will still try to flow in sideway direction. So, for that we will provide another square guard ring. So, we can provide, this is the guard ring is provided. So, guard ring is heated with another heater which is H2, and this heater is providing the heat to the guard ring to maintain the same temperature. Suppose this is the temperature 35 degree Celsius, here also exactly 35 degree Celsius temperature we are maintaining. So, this heater temperature, plate temperature 35 degree Celsius, guard ring temperature is 35 degree Celsius. That means, there is no temperature gradient. So, heat will not try to flow from the test plate to the guard ring. So, this side, the sideway flow of heat is being blocked using two technique, one is the cork, insulating cork, another is maintaining the same temperature of guard ring. So, we have blocked the sideway transmission, then another side which is creating problem here, heat can flow in bottom sides also. So, here what we do, we provide another plate which is called bottom plate, and which is again heated with another heater H3 to maintain the temperature again 35 degree Celsius, same temperature. That means, if we have no temperature gradient, so that heat will not flow in this direction also, bottom direction. So, we have blocked heat flow sideway as well as the bottom way, only one direction the heat can flow, that is the top direction, and in the top direction we have placed the fabric on the test plate, and that is how we can measure directly the heat which is flowing through the fabric, and this heat is provided by heater H1. That means, in guarded hot plate we measure the heat which is provided by H1, that is which is heating the only the test plate, and bottom plate and guard ring, the heat which we normally do not take into account, these heats are required to maintain the same temperature. Okay. So, the test apparatus here, the test plate surrounded by guard plate at 4 sides, below it is surrounded by lower guard plate, that is bottom plate, a constant temperature around 33 to 36 degree Celsius. So, same temperature is maintained. The testing atmosphere should be maintained at fixed condition 4.5 to 21 degree Celsius, that is recommended. We can use other temperatures also for different experimentation, and the relative humidity at different range. So, the method is that the specimen is placed on the instrument and is allowed to reach the equilibrium condition. Heat passing through the sample is measured in watt per square meter, that is power consumed by the test plate per unit area. So, if we see this picture, this is the top view as I have already shown. Center one is the test plate, here these are the insulation, and then it is a guard ring, and after that another insulation, and above that we place the test specimen, and below there is another plate which is the bottom plate, and 3 different heaters are used for heating and to maintain the same temperature. Let us see the animation here. In first we will see the only the test plate without any guard plate and bottom plate. This is showing top view and it is side view. The plate is there, above that we are placing the fabric specimen, and then the test plate is connected with heater, and once it is heating, the heat will flow at different direction. But in other animation, if we see, this is the test plate and this is a guard plate and insulation, and then it is a red one is bottom plate. We are placing the fabric specimen, and then these plates are connected with heater, and once the temperatures are maintained same, the heat is only flowing through the fabric specimen, that is recorded, and which is the thermal transmittance is expressed in terms of U value which is the P is the power consumed by the test plate, A is the area of test plate and also the area of fabric, and T p minus T a, these are the temperature difference. Okay. And we can use the bare plate test to know the constant for the instrument, and if we subtract we will get the thermal transmittance of fabric itself. Okay. So, as already explained, the thermal transmittance, also known as U value, is the rate of transfer of heat in watt through 1 square meter of a structure. In this case, in our case it is a fabric, divided by the difference in temperature across the fabric structure. Okay. It is expressed in watt per square meter per Kelvin, and Q is the heat transfer in watt is equal to A multiplied by U multiplied by T 1 minus T 2 is the temperature difference. So, U can be measured as Q by A by T 1 minus T 2. Okay. So, if we try to see the actual fabric thermal transmittance, we can compare with the standard material single glazing like window, it is having 5.7 watt per square meter Kelvin. Okay. Now, likewise we can see the well insulated roof, it has got value of transmittance value 0.15, well insulated wall, it has got value 0.25. Okay. So, well insulated floor 0.2. So, in this way we can get the insulation value. So, 0.15 is the well insulated roof. Now, if we want to compare the insulation value, the insulated roof insulation value with our fabric, we will get this value. The thick oven fabric has thermal transmittance value 20 to 80, that is the oven value. Thin oven value 550 to 200, that is the range we can get, and knitted medium weight cotton fabric is having 30 to 100 watt per square meter. This is the range we will get. So, when we test with the guarded hot plate. So, thermal transmittance is a combined thermal transmittance of specimen and air, which is calculated as U1, which is P by A multiplied by T p minus T a, where T p and T a are the temperature of test plate and temperature of air, ambient air, that is the temperature difference. P is the power loss by test plate, A is the area, and this is actually combined with the air. Now, we can measure the thermal transmittance of air, okay, which is by bare plate test we can do without any fabric, and from there we can calculate the thermal transmittance of fabric itself. So, we have discussed the Togg-meter principle, we have discussed the guarded hot plate principle, and another principle we will just discuss, which is KESF thermolab. Okay. In this system, it is basically here it evaluates the thermal transmission characteristics of fabric. This is simple technique. It measures the ease at which the heat is transmitted from a heated plate with a constant temperature of 30 degrees Celsius. So, there are two plates, one plate is having 30 degree Celsius, in another plate it is 20 degree Celsius. In between that these two plates there is a fabric specimen. This is actually the technique is like that. Here is a plate 1 which is kept at 30 degree Celsius, and then we keep fabric specimen here. This is a fabric specimen, and another plate which is kept say 20 degree Celsius. So, heat will flow from hot plate to relatively cooler plate, and it will flow through fabric. The thermal conductivity K, that is W, the watt per meter Kelvin of fabric, can be calculated using simple formula. Thermal conductivity K is heat flow rate multiplied by distance, that is the thickness of fabric, then cross section, the area of fabric by temperature difference. So, this will give direct value where Q is the quantity of heat flow that from the hot plate to cooler plate, T is the time required, and L is the fabric thickness. Okay. A is the area of fabric and delta T is the temperature difference. So, using this simple technique, the KESF Kawabata evaluation system in Thermolab 2 we can measure the thermal conductivity. So, we will stop here. So, we will continue with this discussion in next class. Till then, thank you.